This is Physics 2211 Lab 4 Oscillations. So the purpose of the lab was to observe and measure the motion of a mass swinging in an arc while oscillating on a spring. We used the observations to create a computational model to measure its change in energy. And this preview of the results is that the predicted and observed motion are more similar in the x direction than the y direction. The potential kinetic energies were opposite in trends, and the total energy is 0. So here are some fundamental principles of Newton's second law. So we have the position formula, and we have the velocity update formula. The forces on the system are the force of spring and force of earth, and that's how we're going to find that's how we're going to find L naught for the code. And we're going to use the energy principle, and the system is going to be the spring, mass, and earth, and surrounding is nothing, so there's no work or energy change. And the energies on the system are kinetic energy, spring potential energy, and gravitational potential energy. And the total energy is adding all of those together. So here's a video of the tracker, and as you can see, we have a mass over here. We have the initial position, initial velocity, oscillation period time, which is 4 oscillations divided by 4, or the oscillation period between 4 oscillations, and divide that by 4. The start time is 0 seconds, the end time is 9.497, and as we said, this is the system, this is surrounding. So the code right here, we have the mass of the ball, we have the initial position, the initial velocity. This is the gravitational constant 9.8, and then we found K using the equation, using the oscillation equation, which is T equals 2 pi square root of m over K, and then we found K. And then right over here, we did that the force of gravity equals force of spring, and that's mg equals ks, and S is going to be L minus L naught, and we just solve for L naught. So here, this is L, and we have L hat, and S is L minus L hat. Or sorry, the magnitude of L minus L naught. And then the kinetic energy equation is right over here. We have the spring, the potential energy of spring and the potential energy of gravity, and then E is going to be adding all those together. This is our initial conditions. Force of gravity is going to be negative mg in the y direction. Force of spring is going to be negative k times S times L hat, and then F now is going to be adding those together. This is the velocity update formula, position update formula, and then once again we have L minus L naught. And then right over here we have K, which is going to be the equation 1/2 mv squared, and then delta K is going to be K minus K initial, and that's the same for all of these, just like with their specific energy. So this is gravity, and this is potential gravity, potential spring, and the total energy is going to be adding all those energies together. So the comparison of models is that right here we have the spring energy, we have the gravitational energy, and we have delta K, and we have this delta E, which is almost a straight line, but all these forces are going to cancel out with each other. This is the X position, which is much more similar than the Y position. So a little discussion is that UG and US are opposite in sign, and as delta US increases, delta UG decreases, and vice versa. Delta K also oscillates, has a smaller magnitude than the other energies. So as I said, the X position versus time graph shows that the model is somewhat in the X position, but the Y position versus time graph is not as accurate. So the reasons for some errors that we didn't account for any other forces like drag force, we didn't account for any other energies like thermal energy, rotational kinetic energy. There's a lack of consistency when choosing the point of mass during the tracker analysis. So what does it mean? So is the energy principle satisfied? Yes, and that's because all these forces are going to cancel out with one another, and you're going to have a total energy of 0. So when you compare the oscillation period of the X model to the oscillation period of the Y model, the oscillation of X is going to be 1.6625, oscillation Y is going to be 1.49575. Take the difference, and that's going to be the difference between the two oscillation periods, between the two different types of models in the two different directions. So conclusion is that we use tracker to observe and measure the motion of a mass swinging in an arc while oscillating on a spring. We use these observations to create a computational model. The predicted observed models were similar, though there were some differences due to human error, lack of forces and energies in the system, and tracker analysis errors. And the energy principle was applied, and we saw that there was no change in energy, so delta E will be 0. Thank you.